When we picture AI agents in an enterprise environment, we often imagine a single, monolithic intelligence designed to connect to every system simultaneously. This is a psychological default for engineers. When faced with complex workflows, it feels natural to build a single, hyper-capable agent to manage it all. Merging all these functions into one agent creates massive security overprivilege, exposing the network to unpredictable rogue behavior. In technical terms, this is called superagency. A superagent operates with unrestricted freedom, executing cross-system commands without strict limits on its context. Universal execution environments present a severe architectural vulnerability that compromises enterprise security. The alternative is to dismantle the monolith. We replace the superagent with a distributed network of specialized microagents that collaborate. This shift requires an established software engineering principle known as high cohesion. High cohesion means a system's components are tightly focused on executing a single, well-defined objective. In an agentic context, high cohesion dictates that we minimize an individual agent down to one highly specific action. For that single action, we grant only the absolute minimum system access required to complete the job. There are no blanket read or write privileges. Secure enterprise AI is built on these tightly constrained, highly cohesive networks, not on omnipotent central brain. Moving to a cohesive network means we need a rigorous framework to categorize these individual agents, because one architectural size does not fit all. This diagram shows the matrix we use to evaluate agents, based on two foundational axes: capability and risk. The y-axis represents risk. It plots the potential blast radius of an agent, from limited damage at the bottom to high damage at the top. High damage systems are those with the access required to modify financial ledgers, delete sensitive user data, or trigger external payments. The x-axis represents capability. It moves from low capability, deterministic agents on the left, to high capability, non-deterministic agents on the right. Low capability means the agent follows strictly predetermined fixed actions. It does exactly what it is programmed to do without any independent reasoning. High capability means the agent relies on non-deterministic reasoning. It dynamically navigates available tools and decides its own next steps to solve a problem. Every agent in an enterprise system must be plotted somewhere on this matrix to dictate the underlying security architecture it requires. Let's focus first on the bottom left quadrant: low risk, low capability. A common example here is an internal wiki RAG model. RAG stands for Retrieval Augmented Generation, a process where the AI retrieves specific facts from an external database to ground its responses. This belongs in the bottom left because it performs a predetermined read-only action entirely on non-sensitive internal company data. Now, shift focus vertically to the top left quadrant: high capability, low risk. An internal style guide editor fits perfectly here. It requires high capability because it must use advanced reasoning to evaluate the tone of a document and dynamically rewrite the text. It remains low risk. Despite its complex reasoning logic, the drafts it modifies are purely internal and non-sensitive. Agents with advanced reasoning abilities do not automatically require extreme security architectures if their potential blast radius is tightly contained. We move now to the right side of the matrix, dealing with high-risk systems capable of inflicting significant damage. In the bottom right quadrant, we have low capability, high risk. Consider a finance data extractor. The extreme risk factor comes from its access. This agent connects directly to sensitive corporate financial ledgers. We balance that risk through severe capability constraints. The agent is locked strictly to predetermined read-only summarization tasks. Finally, we reach the most critical quadrant: high capability, high risk. A prime example is an accounts payable initiator. This agent has massive reasoning requirements. It parses incoming invoices, identifies the correct clients, and non-deterministically decides the exact payment amounts. It combines that reasoning with high-risk actions. It executes actual write commands to external financial systems, permanently moving company capital. For systems in this specific quadrant, traditional API security models break down entirely. They demand a completely different architectural approach. An agent's precise placement on this matrix dictates its operational lifespan and state management within your server environment. Look at the low-capability agents located on the left side of the matrix. Because their actions are deterministic and completely predictable, they can be persistent. They are allowed to live continuously in the server environment, ready to execute their single task. The high-capability agents on the right side of the matrix require a different rule set. Non-deterministic reasoning generates unpredictable state changes. Leaving an autonomous reasoning engine running indefinitely creates compounding security risks over time. Therefore, high-capability agents require an architectural standard of ephemerality. Ephemerality means the agent is instantiated strictly for the duration of a single task. The moment it completes the job, it is immediately destroyed. Terminating the agent immediately after its task minimizes the window of vulnerability. It leaves no standing surface area for rogue reasoning or external hijacking. The final architectural variable dictated by the matrix is identity management and system access. Low-capability agents can rely on traditional non-human identities. We secure them using static API keys and predetermined certificates that never change. High-capability agents require dynamic access. With dynamic access, permissions are never granted as a blanket right. Instead, access is assessed path by path, based strictly on the agent's current reasoning context for that specific moment. Let's return to the high-risk, high-capability quadrant, our accounts payable initiator. Even with ephemerality and dynamic access in place, allowing fully autonomous execution of a high-risk action is architecturally unacceptable. We introduce a mandatory final safeguard, the human-in-the-loop checkpoint. In this secure workflow, the agent executes its reasoning and prepares the financial action, but it is hard-coded to halt before execution. A human verifies the agent's proposed path and explicitly grants manual permission for the transaction to complete. This specific workflow bridges the gap between leveraging advanced AI reasoning and maintaining strict enterprise compliance. Secure, intelligent enterprise systems require highly cohesive, meticulously categorized, and rigorously constrained agent architectures.